The Big Bang is the name scientists give to the moment, about 13.8 billion years ago, when the entire universe was packed into an extremely hot, extremely dense state and began expanding. It was not an explosion that happened at one spot inside empty space. It was space itself starting to stretch out, everywhere, all at once. This idea exists because two hard pieces of evidence needed an explanation. Every distant galaxy is moving away from us, and there is a faint, even glow of heat radiation detectable in every direction of the sky. Without an explanation for both of those facts, nothing about the current universe adds up. Not the amount of hydrogen and helium that exists, not the way galaxies cluster together, not the background heat that shows up no matter where you point a sensitive instrument. The Big Bang model is the only explanation that accounts for all of it at once. Here's what's actually happening when people say the universe is expanding. Space itself is getting larger. The galaxies are not flying through fixed, unmoving space like debris from a blast. The space between them is increasing. This matters because it changes what moving away actually means. If you picture an explosion, you picture something happening at a center point with material flying outward into space that was already there. That is not this. There is no outside space for anything to fly into. There is no center point. Every point in the universe can accurately say every other point is moving away from it, which only makes sense if the space itself is stretching, not if objects are racing away from one shared origin. Land surveyors and GPS engineers deal with a real version of this same fact. Distances between fixed reference stations on the ground can shift slightly over time because of the movement of the ground itself, not because anything moved through the space between them. When a survey crew uses outdated reference data, their measurements come out wrong, and that error carries into construction plans, property lines, and infrastructure projects. The universe expanding means the space between objects is increasing, not that objects are shooting through a fixed background. That distinction is not a technicality. It is the difference between imagining a single violent event that happened once, long ago and far away, and understanding a condition that is still happening right now everywhere, including in the space between you and the nearest star. Redshift is the tool that gives scientists proof of that expansion. When an object is moving away from you, the light it gives off gets stretched to longer wavelengths, which shifts its color toward the red end of the spectrum. The farther the light travels through expanding space, the more it stretches. So the amount of redshift tells you both how fast something is receding and roughly how far away it is. This matters because it lets scientists measure motion they cannot directly see. A galaxy is too far away to watch moving in real time, but the stretching of its light tells you it is moving away, and roughly how fast. A police radar gun measures the change in frequency of a radio signal bouncing off a moving vehicle to calculate its speed, and a weather radar system uses that frequency shift to track how fast a storm cell is moving. If either device is miscalibrated, the speed reading comes out wrong, which leads to disputed traffic tickets or inaccurate storm warnings. Redshift is measured with light instead of a bounced radio signal, and the underlying physical shift, a wave stretching because its source is receding, is real and measurable in both cases. Once scientists could measure redshift for many galaxies, a clear pattern showed up. Objects that are farther away are moving away faster, and the relationship is steady enough to calculate. This relationship is called Hubble's law. This matters because it lets astronomers calculate distances across the universe and figure out how fast the whole thing is expanding, using measurements that would otherwise be impossible to take directly. A structural engineer calculating how much stress a beam can handle relies on a proportional relationship between length and load. More length under the same load means more stress at certain points, and that relationship holds steady enough to build a formula around it. If the engineer ignores that proportional relationship, the load calculation comes out wrong and the structure can fail. Hubble's law gives astronomers their own dependable formula. The farther away a galaxy is, the faster it is moving away, in a steady, calculable proportion. The next piece of evidence is the cosmic microwave background, usually just called the CMB. It is leftover heat radiation from about 380,000 years after the universe began expanding, and it is detectable in every direction of the sky today. This matters because it is not an inference pieced together from indirect clues. It is a direct physical signal that can be measured with the right equipment. In 1964, two engineers at Bell Labs were testing a communications antenna and kept picking up a faint, constant radio noise, no matter which direction they pointed it. They checked the equipment repeatedly, cleaned the antenna, and ruled out interference from nearby cities, assuming it had to be a hardware defect. It never went away. That noise turned out to be the CMB, and their instruments had to be recalibrated to treat it as a real background signal rather than an error to be eliminated. The universe carries a leftover heat signature in every direction, and it was first identified using the same kind of equipment used to detect any other radio signal. That signature has since been mapped in extreme detail by dedicated satellites, and the small variations in its temperature across the sky are what tells scientists where matter was slightly denser in the early universe, which becomes important again a little later. In the first few minutes after the universe began expanding, conditions were hot enough for the first elements to form. This process is called nucleosynthesis, and it produced the hydrogen and helium that make up almost everything you see when you look at stars. Heavier elements would come much later, built inside stars over billions of years, but hydrogen and helium were made almost entirely in those first few minutes. This matters because it explains the raw material every star and, eventually, every planet is built from. A blast furnace only produces certain metal compounds once it crosses a specific temperature threshold, and below that threshold, the reaction simply does not happen. A furnace operator who does not hit the right temperature window gets the wrong material output entirely, sometimes ruining an entire batch. The early universe required its own precise temperature and density conditions before hydrogen and helium could form, and once those conditions passed, the window for that particular reaction closed permanently. For a long stretch after that, the universe was too hot and dense for light to travel freely. Charged particles scattered light constantly, so nothing was transparent. Eventually, as the universe cooled, electrons combined with atomic nuclei to form stable atoms in a process called recombination. Once that happened, light could finally travel in straight lines without being scattered. This matters because it marks the earliest point scientists can actually observe directly. Everything before recombination is inferred from physics, not seen. A fiber optic or radio signal can only carry clean data once interference in the transmission line clears. A noisy line garbles the signal until conditions stabilize, and engineers troubleshoot signal loss by checking whether the transmission medium itself is the obstruction before checking anything else. The universe became transparent to light only once the physical obstruction, free-floating charged particles, was cleared out of the way. Once light could travel freely, gravity began pulling matter together. Regions of the early universe that were slightly denser than their surroundings attracted more matter over time, and over hundreds of millions of years, that process built the first stars and galaxies. This matters because it explains why matter in the universe is clumped into galaxies and clusters rather than spread evenly everywhere. On a construction or landscaping site, water and loose material do not spread evenly across the ground. They collect in low points and increase erosion there over time, which creates uneven terrain. A site graded without accounting for that ends up with drainage and foundation problems years later. In the early universe, gravity pulled matter toward the places that already had slightly more of it, and those small head starts eventually grew into the galaxies we see today. There is a hard limit to how much of the universe anyone can ever observe, and that limit comes from the speed of light. We can only see as far as light has had time to travel to us since the universe began expanding. This matters because it means the edge of the universe is not a physical wall. It is a measurement limit based on time and distance. A satellite transmission from a distant relay station has a built-in delay based purely on distance, and engineers can never receive that signal instantly, only as fast as physics allows. Any system that depends on real-time control over a long distance has to be designed around that unavoidable delay. What we can see of the universe is limited by how far light has physically had time to travel since the beginning, not by any kind of boundary out in space. This is the important part. All of these ideas show up together in a single practical situation, Not just as a list. Picture a telecom company troubleshooting a mysterious, constant low-level noise across its fiber network monitoring system. The engineers first check whether it is equipment error, the same first step the Bell Labs engineers took in 1964 before they identified the CMB. They rule out a hardware defect through repeated testing. Next, they measure whether the noise is uniform across every part of their monitoring array, which is the same signature that separates real background interference from a single faulty node. Then they cross-check the timing of the signal against the known transmission delay for their most distant relay stations, applying the same distance-based limit that defines how far into the universe we can actually observe. Finally, they realize the explanation has to account for a condition affecting the entire system, not one broken part, which requires the same shift in thinking it takes to move from picturing a localized explosion to understanding an expansion of the whole space at once. 4 separate ideas, working together on one real diagnostic task. Here's what people most often get wrong. People picture the Big Bang as an explosion going off at a single point in empty space. This is easy to get wrong because the word bang naturally suggests exactly that. And most illustrations people see growing up show a burst of light radiating outward from one spot. The fix is to hold on to the idea that space itself was expanding everywhere at once, with no outside space for anything to explode into. People also assume redshift means objects are physically flying away like debris from a crash. This is easy to get wrong because that matches the everyday meaning of moving away. The fix is to remember that light is stretching because the space it travels through is expanding, not because objects are racing through a fixed background. Many people think the Big Bang explains where everything came from, including the laws of physics themselves. This is easy to get wrong because the theory sounds like a full origin story for existence, and the name itself invites that assumption. The fix is to state plainly that the theory describes how the universe expanded from a hot, dense state, not what caused that state to exist in the first place. People also confuse the edge of the universe with an actual physical boundary. This is easy to get wrong because every object in daily life has edges, and it feels unnatural for something not to. The fix is to remember that the limit is about how far light has had time to travel, not a wall in space. Understanding the difference between expansion and explosion means you will not be misled by science. Reporting that casually describes the universe exploding outward. You will catch the inaccurate framing instead of repeating it, and you will be able to correct it clearly if the topic comes up in conversation. Understanding redshift means you can follow real astronomy news, including new telescope discoveries, without getting lost when scientists explain how they measured a distance or a speed, which is how most major space headlines are actually reported. Understanding nucleosynthesis means you will know exactly why hydrogen and helium dominate the universe's makeup, which matters if you ever read further into stars, fusion, or energy production, since fusion power research depends on the same basic reaction that built those elements. Understanding recombination means you will know why nothing before that point can be directly observed, only calculated, which explains why scientists talk about the early universe with such different levels of certainty depending on how far back they're describing. Understanding the observable universe limit means that when someone asks what is beyond the edge of the universe, you can explain clearly why that question does not have the kind of answer most people expect instead of guessing or repeating a myth you picked up secondhand. You can now explain why the Big Bang was an expansion of space, not an explosion inside it, and back that up with a real reason instead of a guess. You can now point to actual evidence, redshift, and the cosmic microwave background when someone asks how scientists know any of this happened. You can now describe why the universe is made mostly of hydrogen and helium, and why matter clumped into galaxies instead of spreading out evenly. You can now respond to the question of what lies beyond the observable universe with an accurate answer grounded in the physics of light and time, instead of an easy myth. This is the understanding you should have been given the first time, and now you have it. The next time this topic comes up, whether in an article, a documentary, or just a conversation, you won't be nodding along hoping it makes sense. You'll actually know what's being described.